dear friends, welcome to my channel. My name is Johannes. In this tutorial session, I'm going to show you some examples on cross drainage structures as part 1 on design of transitions, canal, flume, drainage, and highest flood level. So these topics will be treated under this tutorial. So let's see. Before that, we have to see the learning objectives. So by the end of this chapter, students will be able to determine the length of drainage waterway and decide the number of spans and fix the dimension of canal and the number of compartments, and also analyze the total energy level and water surface levels at various points, and design the width of the canal at contracting and expanding transitions using different methods, and select the type of cross drainage works required for crossings based upon the bed level of canal and highest flood level of the drainage, and you will be able to determine the head loss in the canal, especially in the flume sections. So having this in mind, what is a cross drainage structure? So it is a structure carrying the discharge from a natural river or stream across a canal intersecting the stream. So you may just have obstruction for a canal due to river, natural lakes, etc., or different water bodies. So how do you cross this water body or river just for the canal, for water conveyance structure, or sometimes for irrigation purpose? So we have just different systems or types. You may have canal over the drainage, sometimes canal over the drainage, canal across the drainage, or sometimes canal below the drainage, and canal and drainage at the same level. You may just cross. So let's see the details. So these types of cross drainage structures: aqueduct, siphon aqueduct, super passage, canal siphon, and level crossing. So just canal over the drainage. If the canal is above the drainage or the flood discharge, so you have to construct aqueduct or siphon aqueduct. Or else sometimes, if the canal is below the drainage or below the flood discharge, you may construct super passage or sometimes inverted canal siphon. And sometimes if just you have canal and drainage at the same level, you may construct level crossing or inlets. So let's see. So what are the factors? So you have factors which affect the selection of suitable type of CD works. Are the first one is relative bed levels and water levels of canal and the drainage. So you will compare just the elevation of the bed level of canal and also the drainage and etc. So you have discharge of the drainage again, discharge of the drainage. What is the discharge of the drainage? And the size of canal in drainage, and suitable canal alignment. You may have different canal alignments. So to select these drainage types, cross drainage types, you have to see the suitable canal alignment and suitable soil available for bank connections, and also nature of available foundations and permissible head loss in the canal, and sometimes availability of funds. So if you have fund, you may just select depending upon relative bed level and water level of canal and drainage. You can select. So cross drainage photos, you can see this is an aqueduct. So you can see just the drainage is just going below this. You see, this is the drainage, but this is the canal or water conveyance structure. So this is aqueduct. You can see just water is going like this, then it will go like this. Just this is siphon aqueduct. Siphon aqueduct. Just it will go under siphoning action. So you can see this is just like this. It will go under siphoning action. And super passage, you can see just sometimes canal may be just canal may be below. So this is just canal below the drainage. So this is the canal, but the flood is this one. So you have flood discharge above the canal. So sometimes you may construct super passage. So this is, you can see, just this is just super passage. So we have flood here, highest flood level, and canal is going under the drainage. So canal siphon is just under siphoning action. It will go like this. So you may construct just under siphoning action. The canal is going like this. So you may have just water level. You may have a stream or sometimes river. So you may just construct below this flood discharge. So these are just the sample photos for cross drainage structures. So let's go to the detail now. Let's go to the detail. So what are the preliminary data? So you need preliminary data. So before undertaking detailed design of an important CD structures, so you need to collect relevant data for construction of this CD. So the following hydraulic data regarding canal and stream should be made available. So for canal, you need to have discharge, depth of flow, water level at full supply, and bed width of a canal also required, and canal bed slope, and water surface slope, and sometimes levels of canal bed and the top of canal banks, and canal cross sections, and canal just sometimes canal slope, etc., and characteristics of material of bed and sides of the channel. So you need to know the material type, the bed of the canal, and width of roadway, sometimes width of roadway, and type of just type and class of IRC loading also just for roadway on the side you may just construct. So I think these are important aspects just to undertake detailed design of CD work for canal. And for drainage also, we may have for stream or drainage, you need to collect, for example, extent and nature of stream and its catchment. So the catchment area, because flood is coming from the catchment, so you need to know the nature of the stream and also its catchment. And detailed records of rainfall in the catchment. So you need to have hydrological data, rainfall, and just maximum observed discharge also. You need to know rainfall and discharge, and maximum flood level and water level slope as observed under the highest flood condition at the proposed site. And also you need to have site plan of the proposed crossing, including contour. So you need to have contour so that you can understand the terrain nature, whether hillock and sometimes river or flat, etc. You need to identify, and also log of forward or trial pit data to know just the groundwater level, and also just need to have information about the sediment load, and characteristics of bed material, including Manning's roughness and silt factor. Also, we have to know the bed material and waterways provided in road or railway bridges or other hydraulic structures of the area. So these are the basic preliminary data that should be collected before you select the CD work or the CD structure. So having this in mind, now what are the important just for the choice of CD work? The following considerations are important for the choice of CD for cross drainage. When the bed level of the canal is much above highest level of drainage, an aqueduct is the obvious choice. So you will construct an aqueduct if the bed level of the canal is much higher than the highest level of the drainage. So you will select aqueduct. Aqueduct is the best choice. Canal should be higher than highest level of the drainage. And the other thing is just to see if the highest level of the drainage, if HFL is above the bed level of the canal, then a siphon aqueduct is preferred. So if HFL is more than, of the drainage is more than the bed level of the canal, siphon aqueduct will be the best choice. And what else? And you may have again, sometimes when the bed level of the drain is well above the full supply level of the canal, then super passage is provided. So you will just select super passage. And the other issue is if the full supply level of a canal is above the bed level of the drain, a canal siphon is preferred. Just so relative bed level. So when the bed level of a canal and drain are approximately on the same and the discharge in drain is high, level crossing is preferred. So these are the basic considerations which can be taken for the choice of CD work. So this just when relative bed level will be compared, then you can select aqueduct, siphon aqueduct, or super passage, or canal siphon, or level crossing. So let's go to the example now. So a cross drainage. So you are going to design a cross drainage work for the following data and design the transitions by Mitra's method. So you have canal and drainage data, and you will have some assumptions for different roughness coefficient or number of spans, play, etc. So for canal, you have full supply discharge 35 meter cube per second and full supply level 200 and constant depths. Again, you have constant depths. Constant depths of the canal is also given as 1.5 and full supply level 200 already. Canal bed level 198.5 and depths of water you have 1.5 again. Then bed width will be just 22 meter. This is the bed width of the canal. And side slope you have 1.5 to 1 and flumed width. This is a flumed cross section. You have 12 meter and drainage data. You have canal and drainage. High split discharge 350 meter cube per second. It is 10 times. And high flood level 196 and bed level 193.5 and general ground level you have this. So based on relative level of this canal in drainage, you can select the type of CD work, but you have assumptions. Manning rigosity, you have this one, display in contracting transition 2 to 1 and display in expanding 3 to 1, and elasticity factor you have 1, and thickness of pier given 1.5, number of span, you need to fix number of span 10, and span width you have 8 meter. So freeboard in canal 0.5 and the superstructure consists of reinforced cement concrete trough. So these are the given parameters. Now let's just go to the solution. Let's go to the solution. Having this in mind, now we will rush to the silent steps for this problem. So these are the given parameter. Now how do you start? So first you need to have plan view. So this is the plan view. You can see this is the plan view of the canal transition. So you have, this is just canal, which is just contracting transition. Then it will go expansion. So you have section 1 at this point. You have normal cross section. Then you have contracting transition with this curve. Then water is entering to this. Then it will go to this side. So you have fluid portion from here, from B to C, and expansion transition. So you need to compute energy level, total energy level, water surface level, and bed level. So this is the longitudinal section of water level inside this canal. So now let's start solution. So the first step is just step one. Step one will be type of CD work. Since canal bed level is greater than HFL of drainage, which is 198.5, which is much higher than high split level of drainage, which is 196.5, So an aqueduct is the best choice to design the cross drainage work. So this is the first step. Once you just identify the type of CD work, now what will be the next step? Drainage waterway. Step 2 is drainage waterway. So drainage waterway, according to Lacey's theory, you have L 4.75 square root of Q. So this is according to Lacey region theory. So you have 88.86 meter, and number of piers you select. You have number of spans, then you need to subtract 1. So this is 9. The total waterway length between the two abutments will be 10 times span times 8 meter width of the span plus 9, which is number of piers, times 1.5. So this is the total waterway length between the two abutments, and 3.5 meter, which is more than the calculated value, which is 88.86. So it is okay. So you need to decide now. So this is just drainage waterway. So water is going through this. So you have pier. So you have number of spans, 10. So 10 times 8 meter width each, 9, which is number of piers like this. These are piers. 9 times 1.5 thickness of pier. So you get this one. The next step will be canal waterway. So since the fluid width is 12 meter, it is given. Now let's calculate. So length of contracting transition with display of 2 to 1, which is length of contracting transition. Since you are given 22, which is the width, minus 12, which is the fluid width, over 2, which is the ratio, then multiplied by 2. Then you get 10 meters. This is the length of contracting transition. Then again, length of expanding transition you will have with display of 3 to 1. Then you have 22 minus 12 over 2. Then just you have to multiply by 3, which is this 3 to 1 length of expanding transition. So once you just calculate length of contracting and length of expanding transition, now let's see. This is an aqueduct. You have piers. Then you have span, which is 8 meter width, 10 times 8, already calculated here. So the stream is going below the canal. So the canal is above the drainage, and you have flood discharge below. So this is just roadway inspection road on the side. You can construct. Okay. So next step will be, let's provide a trough with 2 equal compartments of 6 meters each, separated by interblade 0.4 meter thickness of wall. So you may have wall. So since you have 2 compartments like this is the canal, and the drainage is just below. Here, drainage is below. So this is 2 compartments. Water level is at this point. Clear? 2 compartments. Then you have wall thickness 0.4 interblade, which is this one. This is interblade wall thickness, and then you have 6 meter span, both 6 meter span. So I think this is just a rough sketch. Now let's see the detail now. Let's see the detail. So let's the side wall be 0.5 meter thick. Could be stone masonry, and freeboard of 0.75 above full supply level of canal, and below the slab of inspection road. Then bottom level of inspection road slab will be full supply level already given. Then plus freeboard, you will add this freeboard 0.75. So you get bottom level of inspection road slab, which is 200.75 meter. Then the entire cross-section of both canal and drainage will be constructed monolithically in reinforced cement concrete, and then let the thickness of trap slab be 0.5 meter. This is thickness of slab, and level of undersluice trap slab will be canal bed level. You have already minus this one. So thickness of slab, if you subtract, then you will have level of undersluice, which is 198 meter. So let me show you. This is just cement mortar wall. Sometimes you may construct concrete. So this is full supply level. This is a roadway. So we are just making this one 2 compartments, and this is the bed. And so we have bearing and RCC. Then you have HFA, which is below the canal bed. So you can see canal bed level minus 0.5. So canal bed level, if you subtract 0.5 thickness of the slab, you will get this one level of undersluice of trap slab, and HFL already given. Then let's continue. Highest flood level of drainage already given, which is 196.5. This is the level of highest flood level already given. Then headway clearance below the undersluice of trap slab, you simply subtract below this one 188 minus this one, you have 1.5. This is headway clearance below the undersluice of the trap slab between this one up to this one. Then length of barrel of canal, you have 12 already, 12. Then this is for canal 12 plus 0.5 times 2. This is just the wall for the canal. 2 compartments you have 2 times 0.5. Then plus 0.4, which is intermediate wall. Then you have length of the barrel, which is 13.4 meters. Then height of the opening of the barrel is a drainage. This is a drainage. So you have 188, which is this one, level of undersluice of the trap slab, minus 193.5. So this is height of the opening of the barrel in the drainage. So height of the opening of the barrel, you have 4.5 meter. So this is, now you can see this is a drainage. This is the drainage. Blood is going below the canal. So this is the canal. The canal discharge is going. So these 2 compartments, 1 and 2. You have 2 compartments here. So the canal is going above the flood. So the flood may just arrive at this point during highest flood level, but we have this 4.5 meter, which is the height of opening of the barrel is a drainage. So this is total height of the barrel in the drainage. Then you can see the elevation and also other parameters. So depth of water in the barrel already, you have highest flood level of the drainage here, highest flood level already given 196.5 minus 193.5. So this is just the bed level of the river bed level. So you have 3 meters, but total height of this one will be 4.5. But the water depth is, or the drainage depth is 3 meters. Okay, so let's go to velocity in the barrel. You have discharge in the drainage of the discharge 350 over area. So area is already depth. You have width. You have 10 number of spans, 10, then times 8. So which means like this. Clear? Like this. So you have 10. 1, 2, 3, etc. It will go up to 10. So you have 10 spans. Each 8 meter width. 8 meter width. And you have height 3. Clear? So you have total area of flow. Total area of flow of a drainage. This one. Then you get 1.46. 1.46 meter per second. So once you calculate the velocity in the barrel, then let's go to design of canal transition. Design of canal transition. So in the transition, the side slopes of the canal will be warped from 1.5 to 1 to vertical. So this is just for canal. Now let's see for canal. So this is just drainage and canal above. Then section 4.4. Let's start from section 4.4. So section 4.4 means just the downstream. So you have transition here, transition you have, then fluid portion up to here, then expanding transition. So water is going, canal is here, drainage is this one, flood below this, clear, below. So this is canal, two compartments you have. Then just in transition, the side slope of the canal will be warped from 1.5 to vertical. So this is just around here. So this is normal dimension. So you will start from section 4. This is 4. This is 3. This is 2. Okay, this is 2. Then this is the first one. So you will start from section 4.4. So section 4.4 means this one. So you will have like trapezium formula, B plus M times Y times Y. This is constant depth. So you will have, this is area of the flow, like trapezium cross section at this point. Then you have this area, then you will multiply again to calculate the velocity. You have discharge in the canal already known. So let's see. So velocity is Q over area. So the discharge in the canal, which is 35 divided by area, you get 0.96 meter per second. The velocity it is, or approach head, V square over 2G, then 0.047, then approximately it will be 0.05. Then total energy level at section 4.4, full supply level you have plus approach head, so 200 plus 0.05, then you get 200.05. And water level already, water surface level is given 200. And bed level will be, you subtract from water level, then you get this result. So section 3.3 will be second step. Total area, it will be in rectangular cross section 12, which is the width of the fluid section, times 1.5 constant water depth. Then it will be 18 meters square. Then velocity again 1.94 meter per second, and velocity head will be this one. Then this is just to show you two compartments you have. Then you have transition here downstream. This is the drainage. Let's see, head loss in the expanding transition. You have this equation. Since you have velocity, so initial velocity square minus second velocity square over 2G, then you get 0.04. Then you can calculate total energy level at section 3.3. At section 3.3 will be just total energy at 4 you have plus head loss from 4 to 3. Then you add. So we are adding. So energy, which just the level of water is increasing, you can see. And water surface level 200.09 minus 0.19, which is the previous. So you have 199.9, and bed level already you subtract again the depth. So we are using the Mitra's method. And section 2.2 area, you have rectangular cross section. Weighted perimeter, you have this one. Since it is volume portion, just we are calculating here at section 2.2. This is section 3.3. Section 4.4 is this one around here. This is 4, this is 3, then section 2 here, then this is just section 1. So we are here at 2. So since this is rectangular cross section at this point, there is no any slope, so you can calculate 12 times 1.5 here. Weighted perimeter for the whole cross section like this. You have 12. This is 12. Then plus 2 times 1.5. 1.5 is the depth of water here. Then 15 meter. 15 meter. Then you can have hydraulic radius, area over weighted perimeter. Then you get 1.2 meter. And the velocity is Q over area 1.94. So the velocity at this point. Clear? Then just velocity is this one at this point, the same with this one, according to continuity equation with the same cross section. So approach head will be v square over 2g, this one, 0.19. Then from Manning equation, this is the velocity, 1 over n, r2 third. Slope, the power of half, or square root of the slope. So slope is just friction loss divided by the length of the channel. Then if you rearrange this one, HF will be v square n square over L square both sides, and you rearrange the equation, you get HF. So HF will be this formula. So if you subtract, if you just have, you get this equation, then finally we have head loss, friction loss between this up to this. Because we are using the length of the channel, which is 93.5 from here, length of the fluid section already given. Then you can just have, total energy level at section 2, total energy at 33 plus head loss, then you get this one, and water surface level will be, just subtract this one, v square over 2g, then you have 199.96, then bed level, which is this one. So these are just the calculations. So this is the drainage below the canal. The canal is over, drainage is below. So we are just calculating. We are calculating now. Section 4 is around here for the canal. Then section 2 here. Section 2. This is section 3. This is section 4. This is section 2. Then you have section 1. This is contracting. You can see. Then expanding like this. Clear? So we are calculating. So energy is just going. So total energy level at section 2 will be, you have total energy level at this point, which is the water surface level, plus the head loss. Then you have total energy at 33 plus head loss between the two. Then you get 200.15. So the depth or the total energy is increasing. Water surface level also increasing. You just have 200 minus 1 minus 100.15 minus 0.19, 199.96 meter, and bed level will be this one, 198.46 meter. So once you compute these elevations, so we are just designing the canal, the drainage of the compartments we have fixed so far. Now let's go to section 1.1, the first one. Section 1.1, which is just, you can see, just 12 times 1.5, 18 meters square. Then weighted perimeter, since it is a rectangular section, when you come from downstream end, then bed width times 2 times y, 15 meter. Then head loss in contracting transition, you have 0.2, which is contracting coefficient. Then v square minus this one, v2 square minus this one. So you have already computed here. Then 0.03 meter. Then total energy level at 1.1, total energy level at 33 plus loss, you get this one. Water surface level, again, you subtract this one, which is this one, the loss, which is 0.05, then 200 minus 200.13 meter. Bed level will be depth constant, then you subtract from water surface, you subtract the depth of water, you get 198.63 meter. So, according to Mitra's method now, for constant depths, we are determining just total energy level, water surface level, and bed level. And determination of bed width according to Mitra's method, you have contracting transition already 10 meter, as we just calculated previously. So using this equation, width at x distance from the origin or from the curve, V naught original dimension, which is fluid width times length of contracting transition divided by length of contracting original width minus x times this one. So we are going to generate for every x we get the width of the channel. So you get this equation. So once you have this equation for contracting transition, then you are going to calculate the coordinate of the parabolic curves from section 2 to is this one. So this you can plot this curve. So since section 2 is this one, so you are just have like this. So this is the contracting transition. So you start x distance from here, just you plot on both sides. You have parabolic curves. You can determine this curve. Clear? This is transition, contracting transition. So once you just design, then you can have construction. So the width bx of the transition at x distance from the origin is this one. So this table will give you to plot the curve. And expanding transition would mean from section 3 to this, like this. This is so section 4 will be at this point. Up to section 4, you are going to determine this curve. Similar. So length of expanding transition already determined 15 meter according to the display of 3 to 1. So you have this equation, similar equation, but you will use this length of transition will be length of expanding transition. So you are going to plot this. You are going to plot this one. Clear? So the width of transition Bx is given by this one. You substitute length of expanding transition with the same equation, but you get this. So once you determine the coordinates of the parabolic curve, this one will be, you can make just if you make narrow, just step size is very small, then you can have smooth curve. So once you have transition, then the next step will be summary result. So summary result, you can have at section 1, you can see canal bed level, at section 2, at section 3, at section 4. So the canal bed level is just increasing, going down. So we can have rough sketch like this. Then water surface level, then total energy level. So you can have section 1, this is section 1, then section 2, then section 3, then section 4. Clear? Section 4. So accordingly, you can have canal bed level. You can start from section 4. We start here 198.5. It is just smaller than this elevation, and just so that the flow is going like this. So this is the water surface level, this is total energy level. So water surface level, you can see just from 1 up to 4, you can see 200.13, then reduce, just slope. So that's why just water is flowing from higher elevation to lower elevation. So you should attain the slope. Slope is going down from section 1 up to section 4. So this is summary result. So I hope it will be easy to compute. So this is a plan view and cross section. Just a detail, you can see canal with 2 compartments. You have 2 compartments. So the canal is flowing and the drainage below. So this is the roadway slope, the roadway slab, and again you have piers and number of spans for determined. So you can see section 1 here, just slope is previously 1.5 to 1, but here splay of this one, just 2 to 1, but here 1 in 3 transition. Then you have canal and drainage below. So section 1, section 2, section 3, section 4. So this is just canal alignment with 2 compartments you can construct, and wing wall you can construct wing wall and road slab and bridge, etc. Roadway slab, and just you have water stop, again important water stop or expansion joint. So this is a general plan view and cross section. So I hope. Thanks for watching. If you have any question or doubt regarding this tutorial, please forward through comment suggestion box. I will reply on it. Thank you.